Hi, today I'm going to be talking to you about MR tractography. MR tractography, or MRT, is a form of magnetic resonance imaging that produces a 3D visualization of the brain's neural tracts. Magnetic resonance imaging, or MRI, utilizes strong magnetic fields and radio frequency waves around the subject through the area that's about to be imaged. So how does MRI work? Image 1 shows the hydrogen protons before imaging. You can see they aren't arranged. Image 2 shows the alignment of protons once the strong magnetic field has been applied by a superconducting magnet. Image 3 shows the effect of radio waves transmitted through the tissue, which causes them to spin in the same direction. Image 4 shows proton realignment once the radio waves are turned off. The time it takes for the protons to realign is measured, and the differences between them are represented as contrast in the final image. How does diffusion tractography work? Diffusion is the spread of molecules in fluid constant with thermal motion. By recording diffusion direction and speed, the direction of the fiber bundles in the brain can be mapped. Once these pathways are mapped, they can be linked to reconstruct connections in the brain, which is how tractography works. Each organ or tissue type shows different times for protons to realign, and they release different amounts of energy. This allows for identification of tissues and can detect abnormalities. How is water diffusion translated into a map? Diffusion within white matter occurs in a single direction, along the longitudinal axis of the axon. This principle is known as anisotropy. This one-directional flow allows for the measurement of the axons to be translated into an ellipsoid, which effectively creates a map of the axons through a mathematical combination of measurements from the different directions. The concept known as anisotropy refers to how the direction of a given material affects its physical properties. This can be seen through the example of wood, where the direction of grain will affect its structural strength. Tensors describe the linear relationships of the axons. They portray the anisotropy of diffusion within white matter tracts and how the different directions correlate and interact. This allows visualization of the magnitude and direction of water molecules within the brain. Tensors can be used to convert the diffusion readings into maps of white matter fiber bundles in the brain. Tensors have a symmetrical layout with at least 6 different elements which correlate to different directions. These are known as eigenvalues. The tensor element with the largest eigenvalue is the direction in which the water will be mainly flowing. This is known as the principal eigenvector. The eigenvector is then assumed to correlate to the direction of the fiber bundle. Mapping eigenvectors is the basis of tractography, as the direction of diffusion shown by the eigenvectors is assumed to be the direction of the white matter axons. When looking at a diffusion tensor color map, areas are color-coded by diffusion direction. Blue represents superior and inferior, green represents anterior-posterior, and red represents left and right. The coupling of MRI and tractography allows us to visualize tracks within the nervous system's white matter using fiber tractography algorithms to estimate neural pathways from diffusion measurements. How significant are developments in MRT? MRT and computer image analysis have opened up an entire new field of research dedicated to the 3D representation of connections throughout the brain. MRT uses very recent techniques as human neural tracts have not been visualized like this before. It's also one of the first methods to observe the function of inner white matter without being invasive. Methods can be used clinically to observe function from any damage of white matter and trace activity within the brain of a patient. MRT has impacted our understanding of how the brain works in various diseases, as measurements can be made for comparing individuals on brain function, behaviour, and where neural tracts originate and terminate. Lesions can be observed, giving great potential for early diagnosis of disease that currently rely on symptomatic diagnosis, such as Parkinson's disease, which is diagnosed through dopamine depletion. This dopamine deficit may be able to be identified early by visualization of the dopaminergic fibers and their axonal loss. An early diagnosis with MRT could make all the difference. MRT allows us to identify the location and impact of stroke or brain tumours. With in-depth visualization of structures, the best route for surgery can be assessed. MRT has opened up developments within the management and observation of a patient's brain in epilepsy. Affected areas can be identified during seizures and the causes can be detected. Pros. The pros of MRT is that it is non-invasive to the patient and all measurements are made in vivo. MRT uses non-ionizing radiofrequency waves, which in comparison to X-rays uses electromagnetic radiation which can cause damage to the patient. Measurements can be made simultaneously during observation. It also uses MRI technology, which is widely used, so its development can be made available to many. MRT is also still young, so there will be more discoveries and advancements to come. So what are the cons of MRT? MRT data is difficult to interpret quantitatively, as it's revolved around the observation of a single patient. There is no current framework to compare and quantify results, due to the fundamental limitation of the measurements, which relies on the assumption that the direction of water diffusion correlates to that of the axons. The mapping method is still relatively ambiguous, where the exact termination points of connections are difficult to determine. MRT measurements are indirect. MRT can be error-prone as well and inaccurate due to noise from MRI, and recorded data can be compromised by pulsation artifacts. And lastly, MRI technology is also expensive. MRT and diffusion tensor imaging is used in many different ways, from observing behaviour and function in the brain by creating three-dimensional maps. Interpreting the acquired data in this field is underway, but it is still a young avenue of research where there will be much development. This gives MRT enormous potential for the study of human brain function and anatomy that will lead to better understanding of the central nervous system, neuroplasticity, neurological diseases, and result in more accurate treatment plans. Thank you for watching.